Hello everyone, welcome back to my channel. This is the lecture number 10th of my data science series. In this video, I will cover the topic dimension reduction. Dimension reduction. What do we understand by dimension reduction? It refers to the process of reducing the number of features in a dataset while retaining as much important information as possible. This is particularly useful when dealing with high dimensional data, which can be difficult to analyze and visualize due to the curse of dimensionality. Dimension reduction helps simplify complex, high dimensional dataset, making it easier to analyze and interpret the data while improving the performance of models. It is a critical step in pre-processing for many machine learning tasks, especially when dealing with large or unstructured dataset. To use dimension reduction. Dimension reduction is a powerful technique in data science and machine learning. Here are some scenarios and considerations for when to use dimension reduction. First one is high dimensional data. When you have a data set with a large number of features, the distance between them data points become less meaningful. Dimension reduction can help mitigate this issue by reducing the number of features while retaining important information. Noise reduction. If your dataset contains many noisy or irrelevant features, dimension reduction can help improve model performance by focusing on the most informative features. Improving model performance. High dimensional datasets can lead to overfitting, where the model learns noise instead of the underlying pattern. Dimension reduction can help simplify the model and improve generalization. Computational efficiency. Reducing the number of features can significantly decrease the computational cost of training and inference, especially for algorithms that scale poorly with the number of features. Techniques of dimension reduction. Here are some of the most common dimension reduction techniques. First, principal component analysis. Second, autoencoders. Third, linear discriminant analysis. First, principal component analysis. PCA is a linear technique that transforms the original features into a new set of orthogonal features called principal components. These components are ordered by the amount of variance they explain in the data. It uses data visualization, noise reduction, and feature extraction. Its advantages are simple to implement, interpretable, and effective for linear relationships. Its disadvantages is assumes linearity and may not capture complex structures in the data. Second, linear discriminant analysis. LD is a supervised technique that finds a linear combination of features that best separates two or more classes. It maximizes the ratio of between class variance to within class variance. It uses classification tasks, especially when the goal is to reduce dimensions while preserving class separability. Its advantages is effective for classification problems and interpretable. Its disadvantages are assumes normal distribution of features and equal covariance among classes. Third, autoencoders. Autoencoders are a type of neural network designed to learn efficient representations of data by compressing it into a lower dimensional space and then reconstructing it. They consist of an encoder and a decoder. It uses image compression, denoising, and feature extraction. Its advantages are can capture complex non-linear relationships and can be tailored to specific datasets. Its disadvantages are requires more data and computational resources, and the architecture can be complex. Benefits of dimension reduction. First is improved model performance, reduced overfitting by decreasing the number of features. Dimension reduction can help prevent models from learning noise in the data, leading to better generalization on unseen data. Enhanced accuracy. Simplifying the feature space can lead to improved model accuracy, especially when irrelevant or redundant features are removed. Second, noise reduction, improved signal clarity. By focusing on the most important features and discarding noise, dimension reduction can enhance the quality of the data, leading to more reliable and analysis and predictions. Third, easier data visualization. Visual representations of data can help communicate insights and findings more effectively to stakeholders who may not be familiar with complex data structures. Fourth, reduced computational complexity, faster training and inference. With fewer features, algorithms can train and make predictions more quickly, which is particularly important for large datasets or real time applications. Lower resource requirements. Reducing dimension can decrease memory uses and computational power needed for processing, making it feasible to work with larger datasets. Types of dimension reduction. Dimension reduction techniques can be broadly categorized into two main types. First, feature selection. Second, feature extraction. Each type has its own methods and applications. Here is a detailed overview of these categories and their associated techniques. Feature selection. Feature selection involves selecting a subset of the most relevant features from the original dataset without transforming them. The goal is to retain the most informative features while discarding irrelevant or redundant ones. Feature selection can be further divided into three main approaches. First, filter methods. These methods evaluate the relevance of features based on their intrinsic properties, often using a statistical test. They are independent of any machine learning algorithms. Second, wrapper methods. These methods evaluate subsets of features by training a model and assessing its performance. They are computationally intensive as they involve multiple iterations of model training. Third, embedded methods. These methods perform feature selection as part of the model training process. They incorporate feature selection into the model itself. Feature extraction. Feature extraction involves transforming the original features into a new set of features, often in a lower dimensional space. This process can capture the essential information while reducing dimensionality. Its common techniques are linear techniques, principal component analysis. It transforms the data into a new set of orthogonal features that maximize variance. Linear discriminant analysis, a supervised technique that finds a linear combination of features that best separate different classes. Second, nonlinear techniques, de-distributed stochastic neighbor embedding, a technique for visualizing high dimensional data by preserving local structures in a lower dimensional space. Third, neural network based techniques, autoencoders, a type of neural network that learns to encode the input data into a dimensional representation and then reconstruct it back to the original space. Fourth, matrix factorization techniques. Singular value decomposition decomposes a matrix into three other matrices, often used in collaborative filtering and latent semantic analysis. I have explained the topic dimension reduction. For understanding other topics, stay tuned for further videos. Thank you.